I'm Julian Rosman from Saarland University, and today I will present our divergence analysis. To keep everyone on board, I will first explain SBIMD divergence and reducible control flow graphs, then I will show you what our analysis tries to achieve and how it does that. For a detailed discussion on why we achieve the desired result, you will have to consult the paper. Let's start with a short introduction to SBIMD programming. SBIMD stands for Single Program, Multiple Data. It is an important parallel programming paradigm, and it is predominant in GPUs. Some of the well-known SBIMD languages are CUDA and OpenCL. A SBIMD program is instantiated n times. These instances of the program are often called SBIMD thread or vector lane. These n threads are executed independently. Whenever computations depend on the particular thread ID, then particular threads can depart from each other, as it is seen in these 4 traces in our example. We call a variable varying if it depends on the thread ID. In this case, it can have different values on different threads. A variable that is not varying is uniform. Here you can now see a real-world example of an SBIMD program. It's an OpenCL kernel that computes the discrete cosine transform. The actual computations don't really matter here. What is important is that the branch predicate inverse does not depend on the thread ID, and thus it is uniform. In this case, either all threads pass the then part or all threads pass the else part of the conditional. In this case, a SBIMD compiler can exploit this information to generate better code. We will see that on the next slide. Think about our previous example and now assume you want to generate code for a machine with vector instructions. In this setting, the compiler generates one program which is then executed in m instances simultaneously using vector instructions. If you don't know whether the branch predicate at B is uniform, some threads may go to C and others may go to D. So the generated code must actually execute both C and D. In essence, the compiler has to linearize the entire CFG and generate additional code to mask out redundant computations. If B is uniform, this is all unnecessary work, because actually all threads go either left or all threads go either right. To avoid this overhead, good SBIMD compilers do a uniformity analysis to determine which variables are uniform. If B is proven uniform by a uniformity analysis, the compiler may retain the control flow branches, prevent linearization, and reduce the amount of masking code. In total, this increases the efficiency. One main goal of our analysis is practicability. This is why we choose as model of computation control flow graphs, or in short CFGs, because they are used in intermediate languages of low-level compilers like LLVM. The name basically explains how they work. They all have a root as an entrance point, and the computations are done along the edges. Assignments on the edges may change the state, which is just a map from variables to values. At branches, branch predicates determine the flow. In particular, loops are also possible, but we have to enforce a restriction on them. We require a property called reducibility. In a reducible control flow graphs, loops are always entered through the same node. This node is then called the header. For an irreducible control flow graph, you actually would need a goto to jump inside of a loop, like in this crossed out example. And since this practice is highly discouraged, if even possible in most programming languages, almost all control flow graphs are actually reducible. The existence and uniqueness of headers allow for counting the iterations of the loop, which will be important later on. But there are also other topics that are interested in a uniformity analysis. For example, non-interference is very related. In non-interference, we want to separate secret data from public data. Consider this example. We assume C is a secret variable, so it might be a part of a password or something. And the question now is whether X, the output of X, leaks information about C. It turns out that this is actually the same question as asking whether X is uniform at P when C is varying. So we can treat secret variables as varying and public variables as uniform and solve non-interference using a uniformity analysis. There's also one other domain which is interested in uniformity, and this is the binding time analysis that is subject of interest in partial evaluation. In partial evaluation, we assume that inputs are either static or dynamic, so the static inputs are already given at compile time, and the goal now is to find which code is evaluable only with the static inputs. So the question from before, translated to this setting, is whether we can evaluate f of x statically if we know that c is a statically known variable. So here, static corresponds to uniform and dynamic corresponds to varying. So if this topic is relevant for 3 domains, why another paper on it? Indeed, there's a lot of related work. On this slide, we list the most relevant publications for our work. In paper, there is a detailed discussion on related work. Here I will just state why the previous work is either not applicable in our setting or is significantly improved. Control flow graphs as a computational model are crucial for the use in low-level compilers like LLVM. In contrast, this first block is defined on inductively defined syntax, so for example on if-then-else blocks and while blocks, and this is in general just not applicable in a low-level compiler. Then there are some analyses that are only sound under severe restrictions. And finally, there are many analyses on control flow graphs that are strictly less precise, in particular on loops, than our analysis. For every work where we make this claim, we give an example in the paper as a showcase for imprecision. So what is missing in literature is a uniformity analysis on control flow graphs with a precise handling on divergent loops. Furthermore, the existence of published unsound analysis at the requirement of a rigorous correctness proof. This is the empty spot we aim to close. Our analysis is formalized and proven in Coq, it is implemented in LLVM and thus practical, and there is no other analysis on control flow graphs that is as precise as ours. To achieve this precision, it is important to get the definition right. Uniformity is a local property on variables. So if we consider, for example, these 2 traces, then X is uniform at D and also at E, because all traces that do reach D or E do agree on their values at this specific point. And all other traces are irrelevant for the uniformity of X at this point. On the other hand, at P, X is varying because we have 2 traces that have a different value at P. So the first idea for a definition would be to say the variable X is uniform at program point P on the trace set T if all traces in T agree on the value of X at P. This definition is already enough for acyclic graphs, but for loops there is still something missing. Let's consider another example to fill this gap. Here we have a loop with a loop counter j, which is incremented in every iteration. The loop is exited as soon as j is greater or equal to n. Now assume n is varying. For example, let's say it's either 2 or 3. So then we get 2 traces. One goes down and exits immediately, and the other one goes down to S, then takes the back edge to B, and then goes down again and exits the loop. So the question now is J uniform inside of the loop? In the first iteration, J is increased on both traces, so there's no divergence yet. At S, now the traces diverge. The first trace, so the left one, exits the loop, while the other one takes the back edge and does another iteration. So in this second iteration of the right trace, there's actually no point in the left trace to compare the value against. So another way to say it would be the left trace doesn't reach the second instance of B or the second instance of C or S. And thus, it should not have an influence on the uniformity there. So this is why we argue that J is indeed uniform at B, C, and S. But then at P, we observe different values for J, and thus there it must be varying. So now, how would we capture this intuition into a definition? We have to somehow distinguish the program points with respect to their loop iteration. The trick to do this is to virtually unroll the loops. For the definition of uniformity, we use a modified CFG where all loops are unrolled. The duplicated program points in this process are annotated by a tag, which is a list of the values of the loop counters of all surrounding loops. So in this example, B, C, and S are repeated infinitely often, and as a tag they get the corresponding loop counter of this loop. In this representation, the back edge from S to B becomes an edge from S0 to B1 and from S1 to B2 and so on. Thus the resulting graph is acyclic, but it is also infinite. Now in this graph, we can draw the traces from before again, and we see that they actually visibly diverge in this CFG and create disjoint paths from S0 to P. This is the same pattern that we've already observed in our acyclic example. Here we also have some split point S, which is the origin of disjoint paths that rejoin at some other node P. We can use this representation to define uniformity. We say a variable x is uniform at program point P on trace set T if for any tag I, all traces in T agree on the value of x at the instance Pi. Given this definition, how do we define our uniformity analysis? We formulate our analysis as an abstract interpretation. Abstract interpretation is a well-known framework for formulating static program analyses and proving them correct. In abstract interpretation, one establishes a relationship between domains which are usually complete lattices. On the one hand, we have the concrete domain C to model the concrete semantics. In our setting, the concrete domain C is the set of all SBIMD executions of a given program. Since an SBIMD execution consists of several threads, C is the set of sets of traces. The concrete transformer F gives the semantics of a program. The abstract domain A is the analysis information. In our case, this is a predicate on program points and variables. The abstract transformer F# defines the actual analysis. It expresses how we get from existing analysis information to new updated analysis information. The connection from the analysis information A to the concrete world C is given by the concretization function gamma. Gamma defines what concrete properties are represented by an element of the abstract space. To prove an analysis correct, one only have to prove local consistency, as it is shown on this diagram on the slide. Intuitively, it means that doing an abstract step subsumes all possible concrete behavior. The proof of local consistency already gives us fixed point preservation. This means that each fixed point of the abstract transformer is a sound over approximation of concrete behaviors of the program. Thus, the analysis is sound. To summarize, abstract interpretation consists of an analysis lattice A, an abstract transformer F#, and a concretization function gamma. For soundness, we only need a proof of local consistency. I've already shown you the analysis lattice, so in the following we will discuss the concretization and the abstract transformer of uniformity. Remember our definition of uniformity. A variable x is uniform at program point P on trace set T if for any tag I, all traces in T agree on the value of x at the instance Pi. The concretization takes an abstract predicate U and returns the set that contains all the sets of traces T such that if for some program point P and some variable x, the predicate U of Px holds, then x is uniform at program point P on trace set T. The only missing piece of the puzzle now is the abstract transformer. The concretization describes what the result of an analysis means, while the transformer defines how the analysis actually works. Our abstract transformer is a function that takes uniformity information, so a predicate on program points and variables, and returns updated uniformity information. The first idea for a transformer would be that a variable x is uniform at program point P if the old uniformity information U classifies x uniform at all predecessors of P. But we've already seen that this is not enough. Consider these traces again. We know that x is uniform at D and at E because all reaching traces agree on their value there. But on P, we do have two different values for x, so x is varying at P. So we cannot conclude from the uniformity at D and E the uniformity at P. We additionally need to require the uniformity of the respective branching variable, in this case C. We call S a relevant split point for P because branching at S may introduce varying variables at P. In general, we say the relevant splits for some program point P are the origins of possible disjoint paths that rejoin at P. If the branching predicate of all these splits are uniform, all traces go the same path, and thus there are no varying variables introduced. Let's now consider our other example with a divergent loop exiting. Here we don't have disjoint paths on the CFG, but we do have disjoint paths on the tagged CFG. So we can reuse the concept we've used to define uniformity to define relevant splits. So we say the relevant splits of a program point P are the origins of disjoint paths that rejoin at P on the tagged CFG. But now another problem arises. We have now defined the relevant splits using an infinite graph, and this definition is used in our transformer. Thus, is it even computable? As it turns out, there is another modification of the CFG that we can use to compute the exact same set of splits. We call it the head-rewired CFG. We can construct a head-rewired CFG using two simple graph transforms on any reducible CFG. First, we remove all out edges of loop headers, and then we reconnect the headers with the exits of their corresponding loops. In our example, this leads to removing the edge from B to C, and instead adding the edge from B to P. Now let's look at our tagged CFG again. Here we can see there are many possible ways to create disjoint paths. But they all originate in some instance of S. On the head-rewired CFG, there's also one pair of disjoint paths to P, and it also originates in S. As it turns out, this correspondence holds in general and also in both directions. Every split for some program point P on the tagged CFG corresponds to a split on the head-rewired CFG of this program point P and vice versa. Proving this equivalence was probably the most involved part of the Cox-Loudness proof. This representation now is well suited to compute the splits in our analysis, because in contrast to the tagged CFG, it is finite and it's also very easy to construct. In the Novell algorithm that is discussed in the paper, to compute these splits, we actually also make use of the acyclicity of the head-rewired CFG. Putting it all together, our local transformer has the following ingredients. If the given uniformity information U classifies a variable X uniform at the predecessors of some program point P, and the branching predicates of the relevant splits of P are also uniform, then X is uniform at P in the updated uniformity information. This is a sufficient criteria for uniformity. But is it precise enough? Let's look at one last example. Here we have a Z defined before the branch, and it is neither used nor redefined in either branch. So the branching should have no influence on the uniformity of Z at P, right? Unfortunately, if C is varying, this definition of the transformer classifies Z as varying too, because C is the branching predicate of the relevant split point S. This is clearly not desired. We prevent this imprecision by combining this uniformity transformer with a definitely reaching definitions analysis. We require the uniformity of a branching predicate only if one branch contains a redefinition of this variable. This is how the transformer is formalized in Coq. The implementation in the LLVM compiler is actually in a more restricted setting called loop-closed SSA. There, this problem just doesn't occur, so this implementation is free of this last intricacy. The implementation in LLVM that we replace is unsound. Thus, we use the old LLVM only as a reference for analysis time. As a baseline for analysis quality, we use the state-of-the-art information flow analysis by Wasserup, Lohner, and Snating. There they use a control dependence approach. We compare analysis time and number of uniform instructions, branches, and loops on the following benchmark suites: SpecAxel, Heteromark, LuxMark, DOE proxy apps, Rodent, and Trilogy. On average, our analysis delivers 5% more instruction uniform than the baseline. There is no benchmark where we deliver less uniformity. The analysis time of our analysis is on par with the old LLVM implementation, and it is 25% faster than our setup with Wasserup, Lohner, and Snating's algorithm. You can find the full discussion in the paper. To conclude, we deliver a divergence analysis on reducible control flow graphs that is proven correct in Coq. To this end, we suggest a novel definition of uniformity, in particular on the uniformity of loops. Our analysis is upstream in the LLVM compiler, which proves the practicability of our approach. Our evaluation shows that our analysis discovers more uniform variables than the state-of-the-art baseline without any analysis time slowdown.